Hello everyone, in this tutorial we'll go over how to simulate a coaxial rotor. Like the previous tutorial, the rotor will be modeled as a simple blade element momentum model disk, and in an axisymmetric domain we'll superpose, put one on top of the other, and to capture the effects of swirl have them spinning in the opposite direction, and look at the resultant thrust and power figures. So as usual, the OpenFOAM configuration files for simulation are in the case directory. The clean script is for your convenience to restart a simulation. The mesh contains the gmesh scripts used to generate the mesh. The README contains everything I'm saying now, as well as compilation directions. This spinning in the opposite direction while keeping the same thrust direction. So having a clockwise and counterclockwise rotating propeller requires modification of the default OpenFOAM source code. In the default, if you put a negative sign on the RPM, it'll change your thrust direction. So it would be impossible to actually have counter-rotating propellers thrusting in the same direction. Well, I guess you could manipulate the lift coefficient data or whatever, but I'm not really sure. But anyways, that would, even if you could, it'd be very inconvenient. In the run script, after you have compiled the changes, the run script will run your simulation, and the source src folder contains the new source code. So first, let's go over the mesh. Alright, here's the outlines of our domain. So what I did was drew a plane first with these squares here, and then extruded it into the wedge shape. So I use the rotation extrusion in gmesh. So at first it's all a plane, and then I rotate extrude the free stream, rotate extrude this disk, and then rotate extrude this disk. And that's pretty much how you create all of the cells. We can take a look at the mesh for your edification. I mean, it's a simple unstructured mesh with a structured mesh in the cell layers, the rotor disk layers. It's a very coarse mesh, as you can see, and it runs relatively quickly. So the only boundary conditions are the wedge boundary conditions in the front and back, the inlet, the outlet, and the tunnel wall. So we can take a look at the gmesh script in some more detail, in case you're confused about it. So this rotor, these are just parameters to define, to modify the mesh. So we have rotor radius. This defines the size of the rotor disk. Rotor separation. This defines the distance between the disk. The domain distance. This defines how far away the boundaries are from the rotor disks. And this tip LC. LC stands for length characteristic, and it defines the grid size. So if you make this smaller, the grid becomes finer. Hub LC is the grid size at the center of the rotor disk. The far LC is the LC at the boundaries of the domain. So anywhere in between your defined LC points, so these LCs are assigned to specific points in the in the geometry. So any space between those points have their Elsies interpolated from all the defined Elsies. This wedge angle is 5 degrees because OpenFOAM actually prefers 5-degree wedges for axisymmetric simulation, so we just make it 5 degrees. And yeah, so we can go through the script here. The Seee is a convenience function where I don't have to explicitly put like 0 or 1 into every one of these identifiers. We can just increment it and automatically have our identifiers assigned. For example, like if I shuffle some of these lines around in a different order, you know, they'll get assigned See's IDs in the order of their instantiation. So it prevents like having to change identifiers whenever you duplicate things, duplicate code, or stuff like that. It's automatically assigned a unique number. So anyways, these points are the outer. Let's see. So these points is rotor 1. You see we have X, Y, Z, and the LC with the grid size. This is optional. If you don't assign one, it's assigned to some default, some large value. And yeah, so this is very basic point generation. Then from these points we make lines, and then if you're having trouble understanding the syntax, I suggest you to go back to my Gmesh tutorial where I make very basic domains and explain the point commands and line commands and type it out in real time so you can see what's going on. So yeah, first I make the first rotor, then I make the surface here. In Gmesh, from the lines you have to make the line loop, and then you define the surface, and then you can make it structured by saying transfinite surface. And then finally you get quadrilaterals by recombining. I do the same with the second rotor, and then I define the domain. Here you can see the domain loop. Here are the here's where I start to define the points and the lines, and again make the same surface, and then one by one I extrude here. You can see the extrude command after the equal sign right here. One by one I extrude them, and the resulting extruded entities are stored in domain entities. So I keep them so I can reference them later. Domain entities, rotor entities 2. And then here we can see like the original plane I made, I am assigning to wedge 0 because it's, you know, it's the one side of the symmetry, one side of symmetry of the wedge, and then the other side of symmetry are newly generated by the extrusion. So therefore, and they're put in the index 0. Now all of these specifications are in the Gmesh manual if you need more reference. And the inlet, yeah, and then the rest of the surfaces, the side surfaces, are in the order that they were drawn. So in drawing the outlet, in drawing the boundary, the outer boundary, I drew the outlet first, and then probably the tunnel first, and then the inlet. So that's why they're in this order in the extruded return value. And so of course we have the rotating zone, we have the downstream rotating zone, which is the bottom rotor, and the domain. So these are the volumes as opposed to surfaces. These surfaces will be used for boundary conditions, and these volumes will be used, well, these will be used to define the where the blade element momentum model forces are applied. Okay, and so let's go over how we let's go over the changes. So I've included the new and original source files in the SRC folder. You can see this is kind of more extensive than the previous one. Basically, we have to interpret the negative RPM the sign of the RPM, I mean, and incorporate that in the direction of the velocity local to the rotor, the blade, basically. So in the code, if you go into the code yourself, you can see that uc.y is the drag direct. I should say the in the perspective of the airfoil, the drag direction component of velocity. So we see this actually isn't changed. There's a slight space variation, so it's the same as the original source. The original source actually does some weird stuff. If the geometric angle that it computed is less than 0, it'll just force it to be a positive angle. So I remove that, and I also removed this part where it'll try to correct the angle to make it a standard, even though like the natural result of the angle computed by the velocity components might be, you know, very unusual angles. They try to force it into like smaller angles, which is kind of weird. So I just kind of removed it. But yeah, so this is one of the there's only really a few important changes to make, and that's to change the sign of the drag direction velocity component depending on which way you're spinning the propeller, which is determined by the sign of the RPM. So this rotation sign is simply a 1 or -1, depending on if the omega, which is the rotational, which is the RPM, if it's positive or negative. So we just apply that here, and also apply it to when the forces are defined, and that's pretty much it. These other changes are from just post-processing and outputting proper power figures. So let's go ahead and try to compile our stuff here. Actually, let me try to just cat it. So first, in order to do this, we'll need root privileges. So let's just do our sudo s here for root privileges. Now this hashtag, you know, you can see we're in sudo mode. So let's copy over our new source file. Let's go to the FV options folder. So I'm not compiling all of OpenFOAM. That would take a really long time. I'm just compiling the smallest part. I need only the part that's modified, the smallest portion, and that happens to be the FV options folder. So you just do the compilation command wmake, and it just takes a little while. By the way, if I'm being very too thorough, explaining things in too much detail and taking too much time, please let me know in the comments. So let's exit that, and we'll be back at where we were originally. And the changes have been incorporated, and we're ready to run the simulation. So this run script, it generated the mesh for us, it modified the boundary conditions for us, and ran the simulation. So here you can see the converged results. We have this power is in watts for this small slice of rotor disc. The lift is in newtons. Well, I mean, if your units in your mesh were in meters, then the units that I just said are true. You could see that the top disk has a positive drag, while the bottom disk has a negative drag, which means, which sort of confirms, you know, that they're spinning in opposite directions. And another interesting thing is it prints out the maximum seen angle of attack at the along the blades. So you could see like the minimum that was seen was 1.2 degrees and the maximum was like 31 degrees. And yeah, it's interesting to kind of see this, and helpful for any sort of first order design you may be using this for. And on the bottom rotor, we see that we see what we expect. The bottom rotor being in the downwash of the top rotor and being of the same geometry, it produces less lift. As you can see, 0.19 is less than 0.26, and takes less power. 2.6 is less than, but it's less efficient. So 0.19 over 2.6 is less than 0.26 over 3.1. That's perfectly consistent with our expectations of a coaxial rotor configuration. So like last video, let me just take a peek at the configuration options. Configuration options for our propeller. So like last video, we have this disk section, and we can specify the RPM, tip effect, number of blades, all that, and then we just repeat this specification for the downstream disk. So it's basically just a copy. The identifier here, remember, is the cell zone, which the name of which we gave in the Gmesh script. So the downstream rotating zone, if you remember, and the rotating zone were our names. And I use the same profile, so this is the lift-to-drag ratio. The CL and CD versus angle of attack data. So you list them in order, and any angle between any of the points you list will be linear interpolated from the closest. And yeah, same with the geometry. It'll be linearly interpolated from whatever you specified. So just to repeat, like this is the non-normalized distance along the blade, the angle of attack at that point, and the chord at that point. So here you can see at the root I have 30 degrees and 0.038 chord, and at the tip I have 2 degrees and 0.0125 chord. And this is the angle of attack, the coefficient of drag, and the lift coefficient. Okay, and as you can see, this has a positive RPM and this has a negative RPM. So let's take a look at the post-process results. We can confirm that we have counter-rotating propellers by looking at the velocity at the tip of the propellers. So here we can see this is a positive velocity by the color. It's around here, and this is a negative velocity. So they are in opposite directions. But be careful, you have to use the cell data rather than the point interpolated data. As you can see with the point interpolated data, they seem like the same direction, but they're actually not. I think it's probably a bug within the interpolation scheme for a single cell axisymmetric domain, perhaps. But anyways, yeah. So this is the correct one. We do have like a abnormally high velocity here, but it's probably because it's so coarse there. So if we make a finer mesh, we could probably get a more reasonable value there. But anyways, yeah, the flow field on the whole looks very reasonable. You have the stream tube contraction and an increased velocity after hitting the second propeller. Yeah, it's a very coarse mesh, but you can easily get better results by refining this. So yeah, this might be a useful tool for first order estimates of sort of design of a coaxial rotor, like the distance between the rotors, the size of the rotors, the pitch, the taper, the twist or taper of the rotor, and all sorts of things, as well as the airfoil performance data. It might be good for maybe not absolute thrust and efficiency figures, but probably relative ones would be reasonably would be reasonable. So yeah, I think that's it for this tutorial. Remember, everything I have gone over in this video you can get from the GitHub link in the description. I try to make it as easy as possible for you to reproduce what I've done here. And if it's not, if you see there's some obstacle that I can assist with, then please let me know in the comments. Thanks for watching.